This is the fifth lecture in the takeoff performance. In this lecture, we will try to estimate the stop distance and also introduce the idea of balanced field length. And we know in the case of engine failure, there is a decision speed during the ground run, which is notated as V1. So if the one engine failure happens when the ground run speed is larger than the decision speed. Usually, the takeoff should continue, and then once in the air, the pilot will deal with the problem. If the airspeed is less than v1, so there is sufficient distance for the runway to brake the aircraft. So in this case, the takeoff should be aborted. And as for the distance in the case of engine failure, there is a balanced field length. So in this case, the balanced field length is defined as a distance needed to complete the takeoff is the same as the distance needed to stop. So um, then this defines a balanced field length. And we can see there are some typical balanced field lengths for different aircrafts. We can see for Airbus A320, and the balanced field length is about 240 meters. And for the jumbo jet Boeing 747, it's much larger. It's about 3,300 meters. So you can see the typical examples. Now we are trying to estimate the distance to stop. And on the right hand side, we can see the force diagram acting on the aircraft. So we have lift and weight. Along the runway, we have the thrust, and we have drag and also friction drag F, which is equals mu times W minus L. So that's a Newton friction law. Okay, so in order to stop the aircraft to brake, and the thrust is usually 0, so engine usually we need to stop the engine, and the friction is mu times W minus L. Okay, according to the force diagram and applying the Newton's second law, on the left hand side is acceleration times the mass m times dv over dt equals minus d minus f, because acceleration is opposite to the um, drag and friction. So we define along the runway is a positive direction. Okay, so then we replace F by mu times W minus L. Okay, so finally we can have dV over dt explicitly. On the other hand, we have the airspeed, which is ds over dt. That's the definition of velocity. So we rewrite the equation dt over equals ds over v. Okay, so now we are replacing dt by ds over v in the above equation, and then we can have this relation. So v times dv over ds, and then we have the right hand side. Okay, so we write ds explicitly, so we have the right hand side. So we have the ds, then we can do the integration against the dv. Okay, so then we have the stop distance, and it's integrated from S1. That's we follow the definition of V1, so we use a notation subscript 1 and then S0. That's the stop distance. So, and then we can integrate against the velocity V1, that's the decision speed, and 0, and that's the final velocity, which is 0. Okay, so we can have the stop distance. You can see if, the arrow we need to indicate there is assumption. So lift and drag does not change with velocity. In this case, we can do the straightforward integration. Otherwise, we can't if the lift and drag changes with velocity, right? So this is a simplified method. Then we have the question. So we have the ds and its relation. What happens when L and D does change with v velocity? So in this case, we can't consider the coefficient as a constant before dv. So we need to do some additional steps. Okay, so we know L, that's the lift, equals half rho v squared times S times CL, and the same for drag. They all change with V. Now their relation with V is here. And what we do is we replace L and D in ds equation. Okay, so then we have this big equation, ds equals, and something about dv. And um, in the coefficient, we have v um, everywhere, basically. Okay, so the distance required for the aircraft to decelerate from v1 to stop, which is v0. And so we have this integration, which is similar as before, but this time, because the term before dv is changes with v, so we can't take it out. Okay, so then we can rewrite it as dv square, integration against dv square. So in the coefficient, we have 1 over something plus something times v square. And if you remember from the calculus, actually this relation we've used in the previous um, demonstration. So if you remember this integration, and I can be integrating to line, and then we have the stop distance can be estimated this way. So this is more precise than the method in the previous step, which assumes L and a D, lift and drag, is constant, doesn't change with velocity. So this is the relation now um, is a more advanced method. Okay, so this is a final slide in this lecture, and we need to know how to interpret this graph. So this is a graph about speed against the distance from start of row, and this is diagram is used to recognize the balance field length. So, and the black curve on top is all engine AEO, all engine operative takeoff. And so that's the um, normal or standard case. But what happens with one engine inoperative, which is OEI, and from that we can, if we pay attention to the red curve, that indicates a balanced field length. So in that case, the balanced field length is 150 meter, and the decision speed V1 is 130 knot. If the aircraft has higher speed than the decision speed, so the takeoff um, should not be aborted, should continue. And then you can see, for example, if the aircraft has one engine inoperative after 30 seconds from rollout, so the balance the distance to take off is about so from 1010 to 170, so about 600 meters, slightly less than 600 meters. So there is not enough distance, and in this case, the takeoff should continue. And if we pay attention to the light blue curve, that's 20 seconds after the rollout of the aircraft. And in that case, time to brake, the distance to brake is from 500 to 720, for example. So it's 220 meters, and that there's sufficient distance. So that we need to abort the takeoff procedure. And the important thing is we need to know how to um, interpret this speed distance from start of row graph, and how to associate with a balanced field length.